what the output here reflects is the number of games out of 431 that can be won or lost based on the flip of a coin. And what they're investigating here is the coin flip a fair way to determine who gets the ball first and what happens in an overtime game in the NFL. So they looked at the results of 431 games to find out, are the results unusual, or does this give like a 50-50 chance of establishing a winner? Well, the point that I want to get to here is shown by this distribution. What does that distribution look like? These are the probabilities of winning like 220 games or 230 games, 240, etc. What's that distribution look like? Yeah, it looks like a normal distribution. So the problem with trying to find, say, the probability of winning 231 games or 235 games or more from the binomial distribution would be this. So if I wanted to determine the probability that x is greater than or equal to 235 from the binomial distribution, let's understand what that would mean. That means the probability that x equals 235 plus probability that x equals 236, on and on and on. And there was a total of 431 games. So you'd have to do that all the way up to x equals 431. Certainly if you had to do that by hand, it would ruin your day. All right. Now, even on Google Sheets, it still takes a little bit of finesse and a little bit of work. So instead of doing either of those, what we're going to do is take advantage of the fact that we can approximate this with a normal curve. And then we can approximate that probability by finding the area underneath that normal curve. Now, in order to do this, there's a couple assumptions that we have to check. So we're going to work in this section to try and decide whether or not we can, and then if we can, then we need to do it, use a normal approximation to a binomial distribution. Now, there's two assumptions that have to be checked here. Beyond just having a simple random sample of size n from your population. We're going to test that it fits. But then there's two additional assumptions to use this normal approximation. The first one is NP is greater than or equal to 5. The second one is NQ is greater than or equal to 5. Do you remember from our work with the the binomial distribution what P represents? Yeah, it's the probability of success. And then Q is really 1 minus P is the probability of failure. So we want NP. Well, NP, that's just their expected value from the binomial distribution. We want that expected number of successes to be at least 5. And the expected number of failures to also be at least 5. So we want NP and NQ to be at least 5. And if that's the case, then we can make a normal approximation to the binomial curve. No surprise, we're going to use the normal curve with the same mean and same standard deviation as our binomial distribution. That mean, you might remember, is n times p, and the standard deviation is the square root of npq. We'll start with problem number 6. So it says, do the following. If the requirements of NP and NQ are both satisfied, estimate the probability by using the normal distribution as an approximation to the binomial distribution. If NP or NQ is less than 5, then state that the normal approximation should not be used. At that point, you'd have to do other things like actually just use the binomial distribution itself. So we'll start with problem number 7, or 6 I should say. We've got a binomial random experiment with n equals 12. The probability of success is p equals 0.7. If p equals 0.7, what's q equal then? Good. Q equals 0.3. So we're going to check our assumptions first. I want to see, well, first of all, we'd have to determine that it fits before we even start thinking about a binomial distribution or a normal approximation to that. But in this case, we're going to jump down to this part. We want to check that NP is greater than or equal to 5 and NQ is greater than or equal to 5. So 12 times 0.7, I think that's going to be 8.4. On the flip side of things, 12 times 0.3 is 3.6. So what's that telling us? Yeah. So because this is less than 5, we can't make our normal approximation. It just won't work. You'd have to find this probability through other means. So can't use the normal approximation. Now there is one little hang-up in using the normal curve to approximate the binomial distribution. And that hang-up comes about because the number of wins or losses, successes or failures, is a discrete number. You have 1 or 2 or 3 or 4 or 5 or whatever. But the normal distribution takes on an infinite number of values. It can be anything. It can be 1.6, it can be 2.8, it can be square root of pi. It can be anything in those gaps. So you're using something which is continuous to approximate something which is discrete. And because of that, there's a little bit of a snafu that we have to allow for. This is called a continuity correction. So that continuity correction basically corrects for the fact that normal distribution is continuous and the binomial distribution is, just discrete values, a 1 or 2 or 3, etc., nothing in between. So when you're looking to set up your normal curve and calculate your probabilities, you're going to get some areas. For instance, you might have something that says at least 235 or more than 235, etc. And what you're going to do in all of these cases is add on a little bit to the area. So at least 235 is here. You're going to add a half. You're going to make this area bigger by 1/2. Let's move down to the next one. More than 235, would that include 235? No. So that really means 236 is where you start. So if I drew my 236, my continuity correction says I want to make that area bigger by 1/2. So I'd move to the left and started at 235.5. At most, 235 would be here. Your continuity correction says add 1/2 to that. Make the areas bigger to 1/2. Now, I can't make the area bigger to 1/2 on the left side of this because it goes out to negative infinity. But I can make it bigger on the right. Last but not least, if I wanted exactly 235, I'd have to make that continuity correction on both sides. So half to the right, half to the left. I'd end up looking up the area underneath this curve between 234.5 and 235.5. So this continuity correction is something we're going to have to deal with. The only time you make this continuity correction is for problems in this section. Unfortunately, people want to do it for like everything. This is the only place you're going to do it, when you're making a normal approximation to a binomial probability. Let's move down to problem number 8. N is 25. P is 0.4. What's that make Q equal to? 0.6. Yeah. Q is, as a reminder, Q equals 1 minus P. So 0.4 from 1 is 0.6. Now, based on the problem, we're going to assume this is already a binomial random variable, that it passes all the criteria of fits. Second thing we want to check is NP and NQ are both greater than or equal to 5. So 25 times 0.4 is 10, and 25 times 0.6 is 15. So both of these are greater than 5. Oh my, now what are we going to do? Well, now we actually have to follow through with the rest of this. That is, find a normal approximation to this binomial probability. So we want to find the probability of more than 9 successes in this trial. Probability that X is more than 9. Now, because this is a binomial random variable, and we're not including 9, what's the next value that we could include? We are going to use that eventually. This is effectively the probability that X is greater than or equal to 10. You can't include 9. So because binomial random variables are discrete, the next number up is a 10. So we want the probability of at least a 10. Would be another way to say this. Let's figure out what normal curve you're working with. So if we're going to approximate this with a normal curve, we want the mean equal to n times p, and the standard deviation equal to the square root of n times p times q. So in our case, the mean was 25 times 0.4, and the standard deviation was the square root of 25 times 0.4 times 0.6. I think that's going to be like the square root of 6, but somebody check me on that. Okay, thank you. So that'd be 10, and the square root of 6 is the normal distribution that we're going to use to make this approximation. Okay, well, let's sketch this out. The mean number of successes is 10. So this is our normal curve, distribute the normal, 10 and square root of 6. We're going to eventually have to find a numerical value for that. Now, probability that X is more than 9 really means we're going to start up here at 10. I want the probability that X is greater than or equal to 10. Now, if that's all there was to this problem, could you answer it right away? probability that x is greater than or equal to 10? What is the probability that x is greater than or equal to 10 on this distribution? %, right? Because the mean separates the two curves, or separates the curve into two halves. So half the area would be to the right and half the area would be to the left. So if that's all there was to it, then wow, we wouldn't even have to do a z transformation. We could just say, all right, well, it's a 50% chance. But there's a little bit more to it. And that little bit more to it is the continuity correction. Continuity correction says I want to enlarge my area by 1/2 on either side. Now, can I make it bigger by 1/2 to the right? No. Thank you. But I can to the left. So we're just going to put in this little sliver of area right here. Make it bigger by 1/2. So effectively, that's 9.5. And now I can do my z transformation and find a z-score, find an area, etc. But the big thing is you have to do that continuity correction in order to get a reasonable approximation to your area. So the z-score is going to be 9.5 minus 10 divided by the square root of 6. So negative 0.5 divided by the square root of 6. Negative 0.204, or approximately negative 0.20. So just a little bit to the left of the y-axis here. Do we expect a probability that's a little bit more than 1/2 or a little bit less than 1/2? Should be a little bit more than 1/2, right? Because this point is a little bit to the left of 0. And 50% of the area is on either side of 0. So I want a little bit more than 0. Okay, so we're going to look up negative 0.2 in the z-table. 0.4207. Is that the probability that we want? No. So we got to subtract that from 1 to get. Thank you. So 1.000 minus 0.4207, 0.5793. Cool. All right, so to recap, we had to be a little bit careful here. When it said the probability is more than 9, really you had to translate to the probability starts at 10. 10 and up above. Now when we drew that area here underneath a normal curve, before we calculated our z-value, we had to do the continuity correction. Continuity correction says you're going to make the area bigger by 1/2 on either end. Now, you can't make the area bigger to the 1/2 out here, but you can over here. And that's what we did. So we went down from 10 to 9.5. The rest is kind of rehashing the stuff we did in section 6.3. Anything else you'd like me to work on to help you understand with this first one here? Problem number 8. Okay, let's try some more. Let's jump up to problem number 18. Kind of an interesting social type of experiment here for us. So it says, based on observed males using public restrooms, 85% of adult males wash their hands in a public restroom. In a survey of 523 adult males, 518 reported that they wash hands in a public restroom. Assuming that the 85% observed rate is correct, find the probability that among 523 randomly selected adult males, 518 or more wash their hands in public restrooms. What do you conclude? Okay, so on an exam, I'll try and make it pretty clear that I want you to do a normal approximation here. And the reason I want to do that is because this is the only time that you're going to have to make those kind of continuity corrections, period. Please don't use them like for everything. This is the only section in which we make a continuity correction. Now, first thing I guess you would have to do is convince yourself that this is actually a binomial random variable. So, what are the criteria for being a binomial random variable? It has to fit. Thank you. So, problem number 18 fits. Do you have a fixed number of trials? Yes. 520, what was it? 3. So, fixed 523. What's the I part stand for? Independent. Now, I'm assuming that these guys are going to be, observed by themselves and not hanging out with their friends, because there is a little social aspect to some of this stuff. But let's assume that the independent assumption holds. How about T? What's T stand for? Two outcomes. Two outcomes, you wash your hand or you didn't. And that's it. Don't have to play around with anything else. Two outcomes. So we got that. And the probability of success. The total says assume that the probability of success of 85% held throughout this trial. So, yeah, the same probability throughout the trial. Okay. One place you would see this assumption fail is if you're sampling without replacement. Then that would change probabilities, and you also lose your independence. Now you can kind of wink and nod at that assumption if your sample size is small compared to your population. So it fits. Let's write down some things here. N is 523. Probability of success is 0.85. Let's check our assumptions here. Want to check that NP is greater than or equal to 5 and NQ is also greater than or equal to 5. So 523 times 0.85, I'm pretty sure that that one's going to be greater than 5. What's Q in this case? 0.15. And again, I'm sure that that one's greater than 5. All right, 78.45. Thank you. 444.55. There's also another convenience about checking your assumptions here. We needed this number anyways, right? That's our mean for this. Then we need to figure out what the standard deviation is. So mu equals 444.55. Standard deviation is going to be the square root of 523 times 0.85 times 0.15. Let's do that all in one go. So on your calculator, hit the second key, then the square root key. That'll give you, or second key and then the x squared key, that gives you your square root. 523 times 0.85 times 0.15. It's about we'll call it 8.17. Actually, you could just use this value here off your calculator to keep a little bit more accuracy. It's about 8.17. Okay, so we've got our normal curve that we're going to use for this. We wanted to find what probability. Let's look back at this one. Let's find the probability that amongst 523 randomly selected adult males, 518 or more wash their hands in a public restroom. So the probability we want is right here, 518 or more. So probability 518. Now should I put greater than or equal to? Greater than or equal to, because it says 518 or more. So you're allowing for the possibility that your probability or the number of people who wash their hands is including 518. It's 518 or more. And that's a little bit different than problem number 8. Problem number 8 started out at more than 9. So we had to round up to 10 to get where the probability actually started. Here, we're not going to have to do that. All right, so the mean was 444.55. So X is distributed normally with a mean of 444.55 and a standard deviation of 8.17. Okay. 444.55. We want the probability that we had at least 518 people. Does this look like it's going to be a really big probability or a really small probability? Really small. Yeah, it's looking really, really small. So 518 is out here in the right tail. And I'm sure that I'm not drawing it far enough out there, but I want to at least draw something so you can see it. Silver color in that little sliver right there. Can I calculate my z-score? Yeah, we got to do our continuity correction before we calculate our z-score. So before we find our z-score, how am I going to change my area? Perfect. You got to make your area bigger by 0.5. And again, this is going to be exaggerated compared to what it should be most likely, but that's all right. So you got to make your area bigger by half. That's the continuity correction. That's the price we pay for using the convenience of a normal curve to approximate a binomial probability. So it'd be 517.5. That's the number that we need to use to calculate our z-score. Z equals 517.5 minus 444.55 divided by 8.17. All right, 8.93. I'm not really going to worry about exactly how that was rounded because it's way off the charts. It's like way out here. So looking at this, I'd have to go across the hallway to draw this, okay? Yeah. So that probability, if you look it up, the area to the right of that on the normal curve is going to be vanishingly small. It's going to be next to nothing. Now, when you do look it up, if you did, you find it, you kind of get this catch-all that the area to the left of anything bigger than 3.55, they're going to call it as 0.9999. But do we want the area to the left of something? Want the area to the right. So 1 minus that, it's going to be, yeah, it's going to be less than 0.00001. No, let's see, 3 O's. 0.0001. There we go. So pretty small. So that area is, like I said, it's going to be really, really small. Less than 0.0001 would be your final area there. So what do you think is going on? You did this survey. If that 85% mark is correct, what do you think is going on with this survey where you have all these guys saying, yeah, I wash my hands? Yeah. There's some guys that are big liars, all right? So as statisticians, you got to be clever about this kind of thing. This is embarrassing information, but sometimes we need to ask people embarrassing questions. So one of the ways that people have come up with to work around this is we'll take a big sample of people from, that are they're more or less equal in a lot of regards, and they'll ask them some basic questions like, if you're from this area, write a 1. If you're from, if you've ever visited a foreign country, write a 1, etc. And ask a bunch of really innocuous questions. And then ask that same set of harmless questions to somebody else, but then include one other one. Do you wash your hands when you use the restroom? And then just ask the respondent for the total. So because that number is hidden in amongst some other harmless stuff, people are more willing to answer honestly. And then what you do is you compare the two groups. Compare their answers, and you can make some pretty good statistical inferences based on the differences in those groups. So it's pretty clever. Hats off to whoever came up with those kinds of ideas. We're not going to have to worry about that stuff here. Our goal was to find that probability. So how are you doing on that probability? Good, bad, indifferent? Okay. Let's go back to another kind of more basic one. Let's do problem number 12. Now these all reflect back to the description up above here, which is find the indicated number, probability of the indicated number of voters, assuming that 100 eligible voters are randomly selected. And let's see, where's the probability of success? 22% of them voted. Wow, you guys aren't very good. 22%? You're so lazy. All right, just kidding with you. We want to find the probability of exactly 19 voters. I wonder if you guys are different. You guys, should we take a survey? How many voted in the last election? All right. Clearly, you guys are head and shoulders above the Census Bureau data for this. All right, so good on you. Probability of exactly 19 voters. Well, let's see. Problem number 12. We're going to assume that this data fits, and let's move down to checking our other assumptions of NP and NQ. N was 100, P was 0.22. What's it leave for Q? 0.78. Good, it's 0.78. And this is a pretty easy calculation. NP, 100 times 0.22 is 22, and that's greater than 5, so we're good on that one. NQ is likewise greater than 5. So our assumptions check. We next need the standard deviation here. So what's the standard deviation going to equal? So sigma equals the square root of n times p times q. Square root of 100 times 0.22 times 0.78. So 0.4142, etc. We'll round this off to the nearest 100 at 0.414. So that's our standard deviation. And up here is our mean. Mean was 22. We wanted to find the probability. Problem number 12 asks us for the probability of exactly 19 voters. Okay, let's see about that probability. On average, you would expect out of 100 voters, 22 of them would actually show up and vote. So X is distributed normally with a mean of 22 and a standard deviation of 4.14. We want to find the probability of getting exactly 19 of them to vote. That's kind of skinny, isn't it? Yeah. So you got to make this bigger by a half on both sides. Now, this is a little bit different than our previous couple because in the previous two examples we dealt with, one of the sides of this area was really out at infinity. So you can't really make it bigger out there, but you can on the finite side. Here, we're going to make it bigger on the right by 1/2 and on the left by 1/2. So it's bigger in both directions. So we're going to go down to 18.5 and up to 19.5. And now we can use this to find our z-values. We have to find both of them. So it'd be z equals, let's start with the smaller of the two, 18.5 minus 22 divided by 4.14. And then 19.5 minus 22, again divided by 4.14. Thank you. So just a little trick here for us. As we do our calculation, you might notice that we have to do more or less the same thing twice. 4.14. Help out if I have this right. So if you hit the second key, then the enter key on your graphing calculators, it'll just bring up your previous calculation. All I need to do here is go change that to a 19.5. And I get my two values, negative 0.845 and negative 0.603. So this one's going to get rounded up to negative 0.85, and this one's going to stay at negative 0.60. I'm just curious to see what difference it would make. It would make if I, instead of dividing by this, if I divided by the rounded number. And I think what it'll mean is it'll be a little bit different here. So if I did 18.5 minus 22 divided by this number up here, what difference does it make? Oh, I didn't like that. Why didn't I like that? Oh, yeah, I'm missing a parenthesis. Insert a parenthesis here. Insert 18.5. All right, so this one would round different. So it's all right. I'll cut you a little bit of slack on your exam, but it's helpful to see your work. Negative 0.85 and negative 0.60 are two z-values. All right, thank you. So when we look those up, I just kind of squeak them in here. Should I be adding these, subtracting these, multiplying them? Good. So 0.70766. Okay. Any last thoughts on this one? Okay. Let me give you some homework, and then maybe we'll go over a few things in advance of our exam. This is section 6.7. Homework, try problems 1 through 19. And of course, as usual, that's just the odds.